Hey Todd. Hey Todd. Hey Todd. Hey Todd. Hey Todd.
Yeah. Hi Kenny.
How are you doing?
Great. How about you?
Doing great. Doing great. We've got people trickling in from the break, and so we can probably go ahead and get started fairly quickly. I think that we're up to about 88 people, and after we hit the 100 threshold, we can go ahead and begin. I think our audiences have been consistently significantly over 100, and so I think 100 is a safe number to start with. But yeah, so for everyone that's here, I would love to introduce you to Todd. Many of you may already know him, may have already seen his face from various other conversations and talks that he's given around the world on cryptography. In those talks, right, he's been specifically focused at a very high level on describing zero-knowledge proofs, what they are, an analogy using the infamous Rubik's Cube. And today he's going to dive much deeper into the technical aspects of some of the things that he's working on. And specifically, we're going to be talking about Poseidon and Eclair. So without further ado, I'm going to pass the mic over to Todd, and please begin. Thank you, Todd.
Thank you, Kenny. So good evening, everybody. My name's Todd, and I'm a cryptographer at Manta Network. I'd like to go a little bit deeper into Eclair by showing you how you could implement the Poseidon hash function. So my goal for the day is to kind of explain where Eclair fits within OpenZL and hopefully convince you that it's worth using for your own ZK app development. So Eclair, the acronym, stands for Embedded Circuit Language and Intermediate Representation. And something that you may have gathered already from Brandon's talk earlier in the day is that part of the philosophy in OpenZL is that we're going to separate the description of a gadget from the way that we execute that gadget in zero knowledge. So you see in this diagram here that along the top you have some familiar concepts: accumulator gadgets, hashing gadgets, commitments. And along the bottom, you have what I hope are some familiar proving systems: ArcGroth16, Plonky2, things that we heard about already from Pratyush and we'll hear about later from Sebastian. And this middle layer is Eclair. And my goal is to sort of explain to you how it is that Eclair allows the abstract description from the top layer to meet the concrete execution down at the bottom layer. So the idea is that your circuit should be described abstractly in Eclair. It's a language for writing circuits, and the description that you have written in Eclair would then be executed in some kind of ZK proof system, by which I mean that we would generate a witness and a proof according to the logic of some ZK proof system. So that's what these plugins at the bottom are for. They're for generating proofs in the ArcWorks implementation of Groth16 or in Plonky2. And what you can think of is that these proof system plugins are there to compile Eclair code to a ZK proving target. Now, one of the great advantages of writing your circuits in Eclair is this flexibility that you have about which proof system to use. So you've written your circuit in Eclair and you want to use Groth16 as the prover, well, then you can use the ArcGroth16 plugin, right? Or if you decide that you'd rather use Plonk, perhaps you want to avoid the phase 2 trusted setup, well, you would use the Plonky2 plugin, right? And let's say that a new proof system comes along. Well, then we write a new plugin for that proof system, and we automatically get to start using all of our old gadgets that we described in Eclair in that new proof system. So how do we do this? The main abstraction that we use to achieve that is something we call the compiler abstraction. So I'd like you to think of a ZK proof system as being a compiler that takes Eclair code and compiles it to some constraint form, right? Now, each ZK proving system has its own constraint form, has its own notion of variables and allocation and constraint generation. And so what we have is this abstract compiler type that we call COM. And what the COM type does is it specifies in a given proving system, how do we generate constraints, right? How do we then execute Eclair code, right? And when I say execute eclair code, I mean generate a witness and a proof in some ZK proving system. So visually, the main difference that you'll see when you look at eclair code compared to Rust code is that function signatures will have a mutable reference to this compiler type. So let's start with a really simple example. This is the add trait. And on the left, you see the Rust version of the add trait, where you specify some output type for addition, and you define the behavior of the add function. Now, Eclair's version of the add trait is almost identical, except that in the trait declaration, you see that there's this generic com type. So this is how we're going to specify the compiler type. And you see that the signature of the add function contains this mutable reference to a compiler. Now, what this means concretely is that when the add function appears somewhere in our Eclair code that describes a gadget, the compiler that has been passed into the add function will allocate a new variable for the output, and it will generate constraints that force that variable to be equal to self plus right-hand side. So the compiler argument is a way for, if you will, it's a way for this ZK proof system, for its constraints to sort of witness what's going on around them as we describe the circuit and generate constraints accordingly. Something that's worth pointing out is that in the trait declaration, we've specified a default type for the compiler. So we've used the unit type, and what the unit type signifies in Eclair is that you're using the native compiler, by which I mean you're not generating any constraints. You're not working in a proving system. You're just executing code on computer hardware, right? So when no com type is specified, Eclair defaults to the native compiler, and it hands the job of compilation off to the Rust compiler. However, when you do specify a com type, such as for the ArcGroth 16 plugin or Plunky 2 plugin, then what happened inside of that plugin is somebody implemented the add com trait for a type within that proving system, right? Perhaps the finite field variable type in that proving system. And now what's going to happen is that when we interpret the same Eclair code using that compiler type from that proof system plugin, it's going to generate constraints whenever the add function appears, right? So I'd like to show you that this is able to handle complex gadgets, such as the Poseidon hash function. The Poseidon hash function is probably familiar to most of you, but I'll review it quickly. The way this works is it's a permutation that acts on some state, which is a vector of field elements, right? And this state gets permuted over the course of repeated rounds. Now, in the diagram on the right, which I've borrowed from the Poseidon paper, you get a nice overview of how this round structure works. So what happens within a round is that we start by adding round keys to the state. So these are the constants that I've called additive keys, C0 through Cn. This next step of a round is to apply an S-box, which is something like raising field elements to the 5th power. And then you wrap up the round with matrix multiplication by the matrix that I have written there. So that transforms the vector over the course of this round, and then that transformed vector is what will go into the next round, right? And we iterate this repeatedly until finally we've finished and we've permuted the vector. So that's the Poseidon permutation. So how would you go about describing this in Eclair? If you recall from Brandon's talk, he mentioned that the gadget lives within an environment. So what would the environment be for this Poseidon gadget? I've represented it as this specification trait here. So this specification trait, you see first of all that it's generic over some com type. And the first two things that you need to specify are a field type for the state and a field type for the parameters. Now, in native computation, those would be the same type, but of course, we're aiming for a description that's general enough that it could accommodate native computation and computation within ZK. So in ZK, that first type field, that would probably actually be a field variable type, in whatever proving system you're using. Whereas the second type, parameter field, would more likely be a constant type, right? Now, we're not trying to make any assumptions at this point about how your proving system represents variables and constants, right? We're just saying you need to specify what those two types are. Moving on to the functions, which are just sort of the elementary operations that I described on the previous slide, you see that each of their signatures has this mutable reference to the compiler. And so, like I said, what that means is that when the function appears in our description, it allows the compiler to allocate new variables. Take the SBox, for example, right? It tells the compiler, I need to allocate a new variable for the output of the SBox. I may need to allocate intermediate variables as well for that computation. And I need to apply constraints that enforce that the SBox is computed correctly. Right now, at this level of our description, we don't want to make any assumptions about how that's going to be done. It's up to the implementation of the plugin to specify how SBox is implemented, right? Same goes for matrix multiply, which is one of these elementary functions that I am considering to be part of the environment. So with the environment described like this, we can then say what the structures are. So we need some state, a vector of those field elements. And we need the permutation itself, which is the constants, the additive round keys and the matrix. So once all this is specified, we can start saying, how does a permutation round work in Poseidon? So I said that we start with adding round keys. You can see that in the body of this function, the first thing I've highlighted is this add const assign, and it is taking the mutable reference to the compiler as one of its arguments so that it can tell the compiler, allocate new variables and constrain them, right? Same goes for the SBox, which is the second part of a permutation round, and same for the matrix at the very end. Matrix multiplication at the end of it also receives that mutable reference to the compiler and allocates new variables and constrains them. So you put all of this together and you have the actual permutation gadget. So it would just perform the appropriate number of full rounds, the appropriate number of partial rounds, followed by full rounds. And what I think this illustrates really nicely is how composable the framework is. Because you see that this function permute took a mutable reference to the compiler, and it just handed off that reference to each of the subroutines that occur within the permutation, right? So full round received that reference to the compiler, and it passed it off to the add round constants and the SBox and the MDS matrix. And so constraints are just being generated as we go along, right? And they're being generated according to the logic of whatever compiler we end up using concretely for this. So that's Poseidon in about 5 minutes. I hope it's not too fast to follow. I'd like to talk a little bit about what are the advantages of doing things this way. So the main one that I'm really driving at is this proof system flexibility that we get. So you notice that the description we just went through, it never made any reference to how things work in a particular constraint system or anything like that. It was totally abstract, okay? What we did just now could be coded just from a spec of the Poseidon permutation, right? Now, of course, when we want to actually create ZKPs based on Poseidon, then we would go to one of the plugins, right? So we would go to the ArcGroth 16 plugin or the Plonky 2 plugin. And within that plugin, there would be some implementation of that specification trait that I started with. And when a new plugin comes out, we just have to implement that specification trait as part of that plugin, and we're good to go. We're already proving Poseidon in the new proof system, right? So that's great. That kind of flexibility it keeps development very agile, and it's a huge benefit. Another huge benefit is that all of these versions, they automatically conform to the same spec, right? Including native computation, because they all refer back to this one source of truth for what is the Poseidon permutation, right? They all refer back to the description that I just went through. And so we know that as long as the implementation within the plugin occurs according to the contract, right? As long as add round constant really does do addition, then we know automatically that all of the sort of executions in different proof environments conform to the same spec that we used. And then finally, we have a lot of opportunity for low-level optimization. So to compare, for example, ArcGraph 16 and Plonky 2, you might look at this specification as say that you're writing the Plonky 2 plugin. You might look at the specification and say, well, the SBox is something that I could do very efficiently with a custom gate. So I'm going to use a custom gate for the SBox to save on constraints, right? Well, that's not possible in an R1CS-based proving system, but it is in Plonk-like arithmetization. So, we need to make sure that we leave the freedom for those optimizations to be taken advantage of, and that's exactly what we do with this compiler abstraction. Similarly for the matrix multiplication, right? What's optimal in an R1CS-based proving system is not optimal in Plonk-like arithmetization, and so we leave it to the plugin to go ahead and look at these really nitty-gritty details and make sure that they extract all of the optimization that they can, all while making sure that each of those conform to the same spec. So we think it's a really powerful framework. We use it at Manta, as Brandon mentioned. We wrote our Manta Pace circuits in Eclair, and the Manta Trusted Setup uses a lot of this tooling as well. So I hope that I've convinced you that it's worth checking out. Maybe I've even convinced you to start developing your own ZK apps using Eclair. And if you'd like to learn more, there's an early version of our docs at openzl.org. So thanks for your attention.
Awesome. Thank you very much, Todd, for that presentation. And for those of you that joined us on the break, you should have learned exactly what Eclair was, something that Brendan had mentioned this morning as well. And so it's great that we got that deep dive from Todd. Thank you very much. And in the next session, we will be moving on to talk with Sebastian about Plonky 2. And so I'll be ending the session now.